In this lecture, we'll be going over the tool of the Bayes factor. The reading for this lecture is A Practical Solution to the Pervasive Problems of P-Values by E.J. Wagenmacher. If you have not read this article, please pause, go read it, and come back. The primary topics we'll be going over today are problems with p-values and Bayes factors. In a prior lecture, we went over ways to reconceptualize how to work with the p-value and null hypothesis test statistics. We're going to briefly touch on these topics again with a focus on an alternative utility to evaluating hypotheses. As a reminder, the null hypothesis test statistic, which you typically think of as a p-value, is giving you the probability of the data that you get, given it was generated from a world where the null hypothesis is true. So you have the data you have in hand, you have the assumption that the null hypothesis is true, and this is usually evaluated by comparing test statistics, one where your predictive variables would be generated by a null hypothesis. Often this is just an estimation. And one where you have your test statistic from predictors that you observe, those that you have in hand. And again, in a hypothetical world where the null hypothesis is true, if you run the same experiment multiple times, you'll get data generated under the null. You'll get a test statistic. You do that n many times, thousands, millions, billions, trillions. You'll get a distribution of these test statistic values, which reflect the distribution of values of that test statistic under the condition that the null hypothesis is true. So then what you do is you take the test statistic that you get from your empirical data and you see where it falls on this distribution. The farther out on the edges of the distribution your test statistic falls, the less likely it is that the data were generated from the null distribution. Now, problems with p-values. Remember, your p-value here is just the probability that the null exists. As actually discussed in the Wasserstein article from a prior lecture, it depends on unobservable data or unobserved data. Remember, you estimate that distribution of test statistics under the condition of the null hypothesis being true in a hypothetical space. You don't actually calculate them, although you can with things like permutation tests, but they often just depend on this unobserved data assumption. They depend on subjective intentions, which leads to things like p-hacking. They actually don't quantify statistical evidence. The p-value itself is an existential test, not an evidentiary test. And they are poorly understood by the research community, and thus they are often used in inappropriate ways. In the Wagenmacher's article, he goes over an ideal measure of hypotheses, ideal traits for actually evaluating hypotheses. You would want something that depends only on observed data as opposed to unobserved data. You'd want something that's independent of subjective intentions. So something that can reflect a quantitative value that is irrespective or insensitive to the subjective intentions of those calculating the test statistic. You want something that's a measure of evidence, not necessarily existence. So you want to know to what degree you have confidence in one hypothesis or another. And ideally, it's something that's easy to interpret, intuitive, and most importantly, objective. Essentially, what you want is a probability of a hypothesis. Let's say the probability of the null hypothesis being true given the data that you have, which is an evidentiary proof, not the probability of the data that you have given it was generated from the null hypothesis, which is an existence proof, the typical p-value. In an ideal world, an ideal measure of hypothesis evaluations would have these qualities. One statistical tool that meets this definition is the Bayes factor. The Bayes factor relies on conditional probabilities. It relies on Bayes' theorem. As a reminder, this is something we've gone over before. Bayes' theorem is that the posterior probability of a hypothesis given the data is equal to the likelihood which is the probability of the data given the hypothesis, times the prior, which is the probability of the hypothesis, over the marginal probability of the data. If we set the marginal probability to 1, which is basically assumption that you're seeing all the data that you can see, then the relationship between the likelihood and the prior determines the position and shape of the posterior distribution. Bayes' theorem allows for us to test or at least work with conditional probabilities. You can move back and forth between the posterior probability and the likelihood and the prior. Now, remember, in the context of a p-value, the p-value is the probability of the data given that the null hypothesis is true. So it is a likelihood estimate. Ideally, what we want is a probability of the hypothesis itself given the data, the posterior. The fundamental logic of a Bayes factor is using Bayes' theorem to invert the conditional probability question from a likelihood to a posterior. Let's think about this in the context of a Gaussian linear model. So this would be a model that we've seen in other lectures before. So we say f hat of x is the intercept plus the sum of all the regression coefficients against every x. So the likelihood, which we've worked with before, is the probability of y given f of x. And that is just, since we're assuming Gaussian, it's the sum of all the residual sums of squares. Now remember, this is the log likelihood here because we're using sums. So the calculated likelihood of your data given the model, which is your hypothesis, can be calculated in this form in a Gaussian linear model. Now, what's the prior? Prior is a little tricky. In cases where you actually don't know what your model should be, it's safe to assume an uninformative prior or a uniform distribution. Alternatively, if you have a reasonable assumption of your model factors, so for example, you have a set of prior experiments on the same task or same condition that return the same regression coefficients, then you can take that distribution instead as your prior. For example, you would assume that you have some normal distribution with a particular mean or particular variance of your betas. And so to calculate out the posterior probability of your model given your data, or your hypothesis given your data, works out just using algebra. So again, we're going to take the log form here, and the posterior probability of the likelihood that we've worked with before is negative n over 2 log 2 pi minus n log sigma. Those are just taking the logs from the likelihood function, minus the sum of I equals 1 to n of every observation yi minus your model, squared, over 2 sigma. That gives you the probability of your model given the data. This is essentially the concept of the Bayes factor. The Bayes factor takes those probabilities, or tries to estimate the probability of your hypothesis given the data, as a ratio of evidence against two hypotheses. And the ratio of evidence is the key part here. For example, if we wanted to calculate the Bayes factor of the null hypothesis against an alternative one. So we'll use H0 or H0 for null and H1 for a research hypothesis. A Bayes factor 0,1 or BF01, which is evidence for the null against the alternative, is just the ratio of the posterior probabilities for the null distribution over the posterior probability of your alternative distribution. Now remember, by Bayes' rule, the posteriors are just the likelihood times the priors for each. So this ratio of posteriors can be rewritten as the likelihood of your data given your null over the likelihood of your data given your alternative hypothesis times the likelihood of the prior probability of your null hypothesis over the prior probability of your research hypothesis. What this does is it just gives you a ratio of evidence of two hypotheses. It's essentially a likelihood ratio test, but framed in a way as a posterior probability. Now here you can determine the relative evidence for one hypothesis against the other. Now I've presented on the left here the Bayes factor 0, 1. That nomenclature 0, 1 or 1, 0 follows this logic. Any Bayes factor ij identifies whether the observed data are more likely to arise from hypothesis I than hypothesis j. So you're calculating the evidence towards the numerator. Let's go back to our Gaussian linear model here for a second. We can compare two hypotheses. Let's say that you have a simple hypothesis where you think y is a combination of an intercept plus one confounder term, x1, let's say age or sex or some other factor that's not of primary interest to you, plus the weighted influence of your target variable, x2. This could be some task variable of interest. Now the null in this case is the model without your target variable. So just the model with the confound factor. For each model, you can fit each model and calculate out your Bayesian information criteria. This was discussed in the bias-adjusted criterion lecture, where we discussed ways of accounting for models with different complexity. So again, your BIC is basically just adjusting the information criteria from your model based on the number of parameters. In the Gaussian linear model case, the likelihood here is just your residual sums of squares for that model over the total sums of squares. So in the linear regression context, it's pretty simple. So you calculate out a BIC for both the null hypothesis and the target hypothesis, or your research hypothesis. You can then calculate out the difference in BIC values. So if you just subtract the BIC for the alternative against the null. Now notice I'm inverting the order here. So I'm showing delta BIC 1, 0. That'll get important in a minute. Another way of saying this is it's the same thing as taking n number of observations times the log of the residual sums of squares for the alternative hypothesis over the residual sums of squares for the null hypothesis, plus the difference in model parameters. So your alternative model, which is the more complex one, has a p of 1, in this case 2, minus the number of parameters in your null model, which in this case is 1, times the log of the number of observations. It's another way of reframing the difference in BICs here. Now again, just notice that I'm showing evidence for the alternative minus the null. And that one of the reasons is that your alternative hypotheses are often more complex than your nulls. So it will have more parameters. Now the Bayes factor for the null is proportional to the ratio of evidence or proportional to the likelihoods, in this case, if I have no prior, of the data under the null over the likelihood of the data over the alternative. And this, to calculate at the Bayes factor 0, 1 here, is basically just e to the power of your delta BIC 1, 0 over 2. So you take that difference in Bayesian information criteria for the alternative against the null, divided by 2, take it to the power of e. And that gives you your Bayes factor. It is now a quantifiable bit of evidence towards or against the null hypothesis. Now, this particular way of framing the model, with this particular way of calculating the delta BICs and the Bayes factor, are all specific to the Gaussian linear model. How you exactly calculate it for different types of models will vary based on the type of model, but for this example, you can see how easy it is to do it for the linear regression context. The general formulation of Bayes factors, really you can use it to evaluate k-many alternative models. So the example that I showed before was just against one model. But you can actually calculate out a conditional posterior probability for any hypothesis I, given the data, against all alternative hypotheses. So what you do is you just calculate out your e to the negative BIC for that hypothesis. So you calculate the BIC for hypothesis I divided by 2. And that's over the sum of those same calculations for all the other hypotheses. So for all the hypotheses that don't include hypothesis I. So you can now calculate out how an individual hypothesis compares against many different forms of your model. If you want to frame this on the null, on the other hand, you can adjust. The math is pretty simple to show that you could just calculate out from here 1 against many down to just being 1 over 1 plus e to the negative delta BIC 1, 0 over 2. Using this way, this is the direct calculation of the probability of your null hypothesis given y based off those delta BICs. And so as the difference in BICs between your research hypothesis H1 and the null hypothesis H0 gets bigger, the probability of the null hypothesis given your data increases. And you can see this here. So as I shift my change in delta BIC H1 minus delta BIC H0, you start to get essentially a difference in BICs as a proxy for the probability of the null hypothesis being true. As it gets more positive, because remember, you want lower BICs, so lower BICs is better. As this difference gets more positive, you're getting actually more evidence for the null than the alternative. Thus, calculating the probability of the null hypothesis gets stronger. This is a very beautiful technique because now this value, the probability of the null hypothesis given your data, is an intuitive quantifiable term. If I tell you that there is a 95% probability that the data was that the null hypothesis is true given the data that I've seen, you now know how to interpret that. So it makes inference from Bayes factors quite intuitive. There's no equivalent for p less than 0.05 for Bayes factors. So there's not an equivalent version of a threshold for a Bayes factor. That's because the unit itself is so meaningful. The unit values are in probabilities or ratios of probabilities. So you have to make your inference heuristics based off of the strength of the evidence. It isn't an existential proof like a p-value. It's an evidentiary proof. There's degrees of evidence for one model against another. So we typically interpret Bayes factors like this. This is an example of a way of interpreting Bayes factors. So Bayes factor, let's say of 1 to 3, reflects a probability for the null hypothesis ranging between 50% and 75%, which we consider weak evidence for the null hypothesis. As the Bayes factor increases, say from 3 to 20, that reflects a probability of the null ranging between 75% and 95%. And from there, we would indicate that there's positive evidence for the null. 20 to 150, stronger. 95 to 99%. We would call that strong evidence for the null. And greater than 150, well, that's pretty strong. That's 99% probability that your null hypothesis is true given the data. So it's very strong. And I'm talking about this from inferring for the null because that's a useful tool in research. Now, if you have a non-significant effect, if your p-value is greater than 0.05, you can calculate a Bayes factor and tell what's the probability of the null. If it's weak, then you have inconclusive evidence. If it's very strong, you might have a real null hypothesis. Your null hypothesis might actually just be true, and you can make that inference now. So now you can interpret based off of a null finding. You can say there is no effect here, and there's no effect here because the null hypothesis is true. That's something that you can't do with a p-value. For a p-value, if you can't reject it, there's a host of reasons why you might not be able to reject it. But with a Bayes factor, you can calculate out the probability that the null is true itself. So you have strong inferential evidence from it. But you don't treat it like a binary classification. You either have weak, strong, weak, positive, strong, or very strong evidence for the null. You can invert this. You could ask for evidence towards the alternative hypothesis or a range of alternative hypotheses. But I think the utility of Bayes factors in particular are in the case where you're trying to make a decision off of a statistically insignificant effect, where the p-value does not pass your threshold. And you want to know, is it because the null is true, or is it because I'm not well powered enough to answer that question? Those are two very different answers to make future inferences off of. And the Bayes factor allows for you to make that inference. So I hope this lecture's made clear that Bayes factors offer the ability to directly estimate the evidence for one hypothesis over another. This is incredibly useful for making inferences for or against the null hypothesis itself, for actually making inferences as to the likelihood of your null being true that you can't do with traditional null hypothesis test statistics. So this is one more tool to add to your arsenal for inferring your statistical results. Along with p-values, include Bayes factors, so you know not only the existence estimate of a null hypothesis or not, but the evidence towards or against it as well.